Yesterday, we were focusing on looking at defining the five main types of energy. In this unit, we're focusing on what's called mechanical energy, okay? Energy of motion and forces. And so, yesterday we broke down within mechanical energy the three main forms, okay? Just like money can be stored in different formats, so can mechanical energy. Specifically, we have work, potential, and kinetic. Energy of an object's position, an object's motion, or an object's ability to exert a force over a distance on an object. So let's go ahead and break this down, okay? First, we're going to look at work, okay? Technically, you guys really aren't doing any work now, even though it feels kind of painful to be here in school, right? Okay? And that's because we're talking about work, specifically mechanical work, as the product of a force, applied force over distance. So work equals force times distance. That's our equation, okay? Notice you need to do two things in order to have work done. You need to have a force exerted, and you have to put it over a distance. If you don't exert over distance, then no work is done. So for example, when we work out here, I know sometimes when people work out, they'll just kind of hold the weight there until their muscles get tired. But technically, you're not really doing mechanical work. You have to actually move that weight to a distance. You got to lift it there, right? Force over distance. That makes sense? If you hire somebody to shovel snow off your driveway, if they take that shovel and go, ugh, and push hard on the snow, but they don't move it, have they done any work? Not really, right? They're just pushing really hard on the shovel. They got to actually put that force over a distance. Okay? Units for work are kind of goofy. Okay? Normally, you think of force in what when you lift weights? You think of it in pounds. Okay? We're going to use what's called the Newton in honor of this English dude named who? Sir Isaac Newton, right? Okay? And Newton was the guy who actually came up with a lot of our ideas and understanding about motion and forces. So in honor of him, we call the unit of force the Newton. Okay? Just so you have a rough feel for what a Newton is about a fifth to a quarter of a pound. Okay? So an easy way to remember that is when you order a hamburger and you get a quarter pounder, you could say, I want a Newton burger, and they'll look at you like you're weird, okay? But it's about the same there. And then distance is not in feet, but it's going to be in what? Distance in the metric system is measured in what, guys? In meters, okay? So if you multiply 1 Newton of force, about a quarter of a pound, over 1 meter of distance, you're going to get 1 joule of energy, okay? So joule's not a lot of energy, because it's a little tiny measure of, in the case of work, 1 Newton of force over 1 meter, okay? Now what you are used to is what's called calories, with a capital C, okay? But a calorie, a food calorie with a big C is really 1,000 heat calories. It's a kilocalorie. But every time, if you looked at like, a Snickers bar and it's like 140 calories, and if it would have said 140,000 calories, you'd freak out, right? So to make it more convenient, food calorie is 1,000 heat calories. And 1 heat calorie is about 4.18 joules. Okay? Just so you kind of get a rough feel for how energy converts from one form to another. Interesting side note about food calories, okay, and joules and all that, is this is a candy bar from the UK that one of my students brought in once. It's called Fry's Turkish Delight. It actually doesn't taste that great. It's kind of nasty. It's like a really nasty, like Three Musketeers. Though I know some Brits probably like it, so no offense, okay? And here's what I thought was kind of cool. On the back side, under the nutrition information, notice they tell you the actual, what does this say here, guys? The actual energy content of that food. You see that? And it gives it in redneck units and then in metric units, okay? So this is 175 calories, this candy bar. But see how there's a K in front? What does that K stand for? For kilo, 1,000. So this is really 175,000 heat calories, or 175 food calories, which if you multiply that by about 4.18, it's 730. What does kJ stand for? Kilojoules, okay? So I thought was kind of cool is this candy bar actually showed you the actual energy content of that food in both joules and calories, in the metric system, and then for Americans, I guess, okay? Anybody know how they figure out how many calories are in like a candy bar or in potato chips? You know what they literally do? They take a little sample of that food and they burn it, exactly, and they measure how much heat comes out. Kind of interesting there, right? Okay, you guys ever go camping and you throw like potato chip in the fire? Boom! And all the oil burns? Okay, maybe not. Sorry. Mr. Lau's kind of a pyro there, right? And so that's how you see how much energy is literally inside food. Kind of cool, right? Okay, moving on. We need to define what's called weight versus mass, okay? Because this relates to energy when you lift something, okay? And this is commonly confused. That's why I want to distinguish that, okay? Weight depends on how much mass there is on an object, and it depends on how much gravity is present. Your weight depends on where you are on the moon versus the earth. So you know everyone says they want to lose weight after New Year's, okay? You know the ultimate weight loss plan? Go to the moon. You're going to weigh 6 times less, okay? Because gravity on the moon is 6 times less. But really, that's not what people mean, okay? Really, when people say they want to lose weight, they want to lose mass, okay? Mass doesn't depend on the acceleration due to gravity. Your mass stays the same no matter where you are. Mass is how much stuff is actually there, okay? So really, when people say they want to lose weight, what they really want to say is they want to lose mass. You want to lose excess fat in your body or whatever, okay? And actually, one of the health teachers told me technically when you work out and you get more muscle mass, muscle is actually heavier than like fat, right? So if you're actually in better shape, you're actually going to end up weighing more. But in the end, it shouldn't matter. People should love you for who you are anyway, right? Okay? So let me show you a quick illustration here. So as you can see, weight, when you lift weights, literally you're getting a workout because you're resisting the pull of gravity on an object. It's a force. So the units have to be in newtons, okay? So the equation to calculate your weight is you just take your mass and you multiply it by gravity. I don't know if you guys recall, but gravity on Earth, what's that magic number? The acceleration due to gravity. It's 9 point what? 8, okay? So does it ring a little bit bell from our first semester unit looking at free fall and all that, okay? So if you take your mass in kilograms and multiply by gravity 9.8, you'll get your weight in newtons, okay? Whereas mass doesn't depend on gravity, it's just the amount of matter in an object, what's called its inertia, how hard it is to move it, and the units are simply in kilograms. Okay? Moving along. Next, we want to define the second type of mechanical energy, and that's called gravitational potential energy. Okay? It takes work to lift an object against Earth's gravity. So that's why when people lift weights, it looks stupid, right? Like, why is that dude picking up this heavy thing over and over and over? Well, the point is, you're getting a workout because your muscles have to provide energy to lift that weight against the Earth's gravitational field. Okay? That energy is not lost. It is stored in the form of potential energy, specifically gravitational potential energy. Okay? So we could call this GPE, but for short, we'll probably just call this PE later on. Okay? Make it a little bit easier to write. But just to help you remember, we're lifting against gravity. Specifically, we're focusing on gravitational potential energy. So in other words, work is equal to force times distance. Okay? The force you need to exert to lift something is equal to its weight. So the potential energy is equal to the weight of the object multiplied by the height, or mgh. Okay? So in other words, to find potential energy, you can either multiply weight times height or mass times gravity times height. It's the same thing there. Finally, our third form of energy, okay? Last slide for today is looking at kinetic energy, okay? If you push on an object and do work on it, you set it moving, okay? So in other words, if that object is moving, it's capable of doing work on something else. Your energy is not lost. It is transferred and transformed to that object. This energy of motion is what we call kinetic energy. Kine is from the Greek meaning movement. Kinetic energy depends on two variables. One is its mass, and the other is its velocity. But here's what's tricky, okay? The equation is 1/2 mv squared. Notice velocity counts double, counts squared, okay? So here's how this is practical. For example, like in sports, okay? If you're playing hockey, and let's say there's somebody skating towards you, so they have a lot of kinetic energy. Is there any way a smaller hockey player can stop a bigger one? You can, right? What does the little guy have to do? He's just got to skate what? Faster. You see that? And in fact, let's do a little demonstration now with my bowling ball over here, okay?